Hello and welcome. In this video, we're going to talk about valence electrons and how that relates to the charge in coulombs. So the valence electrons are what we talk about when we say that the electrons flow, right? And the valence electrons are the pieces that flow, and they're going to represent these little blue icons that we have across here with the negative symbol on them. And they are the ones with the highest energy levels. They're the ones that get charged the first, and they're in the valence electron shell. And so they are able to leave the shell. They are loosely bound to their atom. Right? Anything within the innermost core layer of the shell is going to be bound to that atom, and that depends on the type of material it is. Sometimes we don't have very many electrons in our outermost shell, or valence electrons, and that's because that material is non-conductive. But if we have a more conductive material, we'll end up with more valence electrons available, and it'll flow current faster. So to get a flow of electrons, we need to have a high potential on one side and a lower potential on the other side, and that allows our conductor to allow the flow across. And so we'll hit play on this. We see that the high potential here starts with our electrons, and the electrons want to get down to the lower potential. They're going towards their opposite polarity. So let's go down one here. The charge in coulombs is directly related to this opposing polarity idea, where the charge is the excess or deficiency of electrons, and that's going to be the positive or negative charge of our electron, of our atom. We'll find that the opposite polarities are attracted, just like magnets. The positive and the negative want to go together, but as soon as you get two negative magnets, two negative polarities, or two south polarities on the same line, they end up repelling each other, and they want to flip over backwards to connect to the opposite polarity. That means that matching polarities will repel, and that's what we see down here. These two positives are going to repel each other, and the two negatives are going to repel each other also, right? They're looking for their opposite polarity. So we're going to measure this difference in coulombs, and we're going to represent it by the letter Q. So the charge, Q, in coulombs is the number of electrons we have divided by this constant down here. This is 6.25 times 10 to the positive 18. That's a really big number. And that's the number of electrons per coulomb of charge. And so we have a bit of a factor here. We're saying that there is a number of electrons that we can expect per charge that we have in terms of coulombs. And if we take, say, number one number of electrons flows through the circuit, we can compare that to the actual number of coulombs of charge that we expect in that circuit. That's going to be very, very small, right? Really small number. If we put a 1 on top and invert that number on the bottom over, we're going to end up with a really small Q number. So that just means that one coulomb of charge is the total charge possessed by 6.25 times 10 to the 18 electrons. It's a lot of electrons. That's why we're going to represent it with this charge in Q. It's going to make it a little bit easier for us to hold on to. One other thing to keep in mind is that the ground is going to be the moment of the lowest electrical ionization. And so that's going to be this uncharged moment up here. There's no forces available when it's at ground because there's no potential left at ground. So that's going to be our most stable version of that single valence shell. Okay, let us know if you have any questions.